Now let's discuss another way for avoiding overfitting. We have learned about linear regression using regularization. This also has um, another name called rich regression. When we train a rich regression model and tune the model on a research, basically we try different values for lambda and store the best model and returns the best model. If lambda is very large, then the width thetas are heavily penalized so that its values are very close to zero. And here we have a case of underfitting. When lambda is very small, and this is like a very much like a no regularization, no control on how the width are varying. So this is a case of overfitting. By trying multiple values of lambda on a grid, we are able to find a value for lambda that gives the best model. Lasso regression. This model is very much similar. The only difference is that it uses L1 penalty. So in the formula, instead of theta j squared, we have the absolute values of theta j. Comparison between lasso and rich regressions. In lasso regression, many coefficients are zero under lasso with high values of lambda. Due to these characteristics, lasso regression is typically used for embedded feature selection. Correlated predictors are allowed in both methods. In rich regression, coefficients of correlated predictors are similar. But in lasso regression, one of the correlated predictors has a larger coefficient and the rest are zero. And that is a good thing for using lasso regressions for feature selection. Lasso regression works well if there are small numbers of significant parameters and the others are close to zero. For example, just a few predictors have influence on the target variable. Rich regression works well if there are many large parameters of about the same values, meaning most predictors have influence on the target variable similarly. A model called elastic net that combines penalties of rich regression and lasso regression to get the best of both worlds. And here in the cost function of elastic net, you can see both L2 and L1 penalties.